Thanks for having me here. I'll be discussing some work that I did with Roberto in Oxford. He's a postdoc there. And we looked at reconstructing dark energy using a statistical method called maximum entropy. And this work is embodied in a paper which was published in MinRAS earlier on this year. Okay, so in the late 90s, they managed to confirm the expansion of the universe. And to the surprise of the Supernova cosmology project, they also found the universe to be accelerating. But according to our precise measurements of the CMB, we also know that the universe is flat. But then according to observations, there was not enough ordinary or dark matter in order to produce a flat universe. And so from this, they inferred the presence of a dominant dark energy component which acted against gravitational collapse. And this is what we dub dark energy. So within the context of general relativity, the Friedmann equations then tell us that this energy density component must then have negative pressure. Okay, so what do we know about dark energy? Well, not much, and it's very worrying because it makes up about 75% of the universe. What we do know is that its effect on the observable universe can be characterized in terms of a parameter called the equation of state, which gives the ratio of the pressure to the energy density. And I just want to emphasize that if we can pin down what W is, it'll give us an indication of what its nature is, and only then can we start hypothesizing as coming up with theories as to what dark energy actually is. So determining W is of great importance, and that's what we decided to try and do. Okay, so most cosmological observations to date tend to want the dark energy to be in the form of Einstein's cosmological constant. So this is where the equation of state is equal to exactly -1, which means that it obviously has no time-dependent properties. So it's a nice, simple solution, but there are many theoretical problems with it. First of all, cosmologists are entirely uncomfortable with the fact that the energy density of matter, which scales with redshift, is of the same order of magnitude as the energy density of cosmological constant, which is essentially constant. And this is a massive coincidence, and it indicates fine-tuning, which makes cosmologists entirely uncomfortable. Secondly, if we compare the measured value of cosmological constant with our most conservative estimates of theory, it's about between 60 and 120 orders of magnitude too small. But another problem with our supposed detection or agreement between observations and cosmological constant is that most results come out of fitting the data to a constant equation of state. And this is very worrying because a time-varying equation of state can be shown to fit the same data as cosmological constant if you choose your parameterization to be constant. Okay, so I've taken an example from Linda's paper where you have two dark energy models which have varying equation of states, which obviously have time-dependent properties. They obviously have a redshift dependence. And what he showed is that both of these equation of states can fit the same data that is apparently in agreement with cosmological constant if you take W to be equal to -1.
I'm sorry, I don't understand what that means, constant parameterization.
Oh, okay, so it's so we're trying to fit W, right? So we take a W and we generate data and we compare it to our data. And if we assume that W has no time dependence and just fit a constant W, W comes out to be very close to -1. So it looks like cosmological constant.
Since time-varying W is you can fit data, what does it mean for W to vary but parameterization to be constant?
Okay, sorry. So for example, if I take this model of dark energy, so I've got a W that varies with time, and I generate data, like hypothetical data in a sense, observables for it, and I compare them to the real data. And that same data, the real data, we've taken and we fitted a W to it, but we've taken that to be constant. We found that they agree.
I see, okay.
Yeah, within 1 sigma error bars. Have I made that clear?
Sure.
Okay. So this just shows how imperative it is that if you're going to try and determine the nature of dark energy, you have to allow for the possibility that it could possibly have time-dependent properties. Why do we care? Well, it's one of the biggest problems in cosmology. It's incredibly important. If we're able to determine its nature, it means we can make predictions about the possible fate of the universe. And it also, what's more exciting is that it may actually be giving us insight into a new type of physics. Okay, this project was born out of the recognition that there are two main problems with dark energy, with determining its nature. The first one is we've got data, but what do we do with it? How do we measure dark energy? And the problem here is going from our observables to what we actually want to constrain. So how do we measure dark energy? We generally measure, well, one way of measuring it is through how it affects the expansion rate of the universe. And that is encompassed in terms of this parameter, which is the Hubble parameter. And you can see this is where dark energy contributes to the Hubble parameter. But our measurements actually tend to be integrals over the Hubble parameter, which is referred to as the co-moving distance r. Now, there are two ways in which we generally probe and get measurements of the co-moving distance. And that's by, first of all, measuring the luminosity distance. DL. DL is basically a distance measure in cosmology, and it tells us how the luminosity of objects changes with the expansion of the universe. So, for example, in an expanding universe, the photons from distant sources become diluted in expanding space, which means that objects which are far away tend to look a lot dimmer than we would expect if the universe was not expanding. If we then take objects of known luminosity and we compare them to how they look to us today, this gives us an indication of how the universe has changed up until this point. And this gives us a measure of the luminosity distance. So we obviously need things whose intrinsic luminosities we know, and this is what we refer to as standard candles, the most typical being the type 1 supernova, type 1a supernova. Another dark energy probe is the diameter angular distance. Again, it's a distance measure. The diameter angular distance tells you how the physical size of objects change with the evolution of the universe. So in an expanding universe, when the objects first emitted their light, they were closer to us, which means that objects far away tend to look a lot bigger than we would in an expanding universe than we would expect. If we then take something of known intrinsic size compared to what it looks to us today, we can extract information of how the universe has evolved up until this point. So we need objects of known physical scale, and these are what we refer to as standard rulers, a typical example being the Barron acoustic oscillation scale. What I wanted to show you through this is that in order to go from our observables to what we actually want to constrain, we encounter an integral. And what's even worse is that if we then want to constrain the time-dependent properties of the equation of state, we encounter a second integral. So this is only if W is time-dependent. And the problem with this is that with each integral, you get an increase in the noise of the parent function, you get smearing of information through the integral, and a massive loss of accuracy. In addition to that, our data sets tend to be quite patchy and quite sparse, with supernova clustered at high and low redshift, which is why we thought that in order to get closer to the nature of dark energy, we have to now start, as much as we don't want to, we have to start concentrating on the statistical methods that we're using to analyze our data to get the information more efficiently and get the most of the information out of the data that we have. So I said there were two problems.
Do you assume flatness here, or are you?
Yeah, we're assuming flatness. Yeah, that's.
Very little you can do otherwise.
Right. Yeah, it does weaken things. But to be robust, yes, possibly we should look at it with including flatness. Yeah, but yeah, it is for flat. The second problem that I was talking about was, okay, now we have the data, what do we do with it? In order to say anything about dark energy, we have to constrain it. In order to do that, we need to parameterize it. Now, this is incredibly difficult given that we have no robust physical theory about what it is. So essentially, what we're trying to do is we're trying to design a trap to catch an animal, but we have no idea what the animal is. So common procedures when we're dealing with dark energy. What do we do with W? We generally Taylor expand it around Z is equal to 0, and then we constrain the expansion coefficients using the data. Sorry. Otherwise, we tend to fit a smoothly varying function to it, such as the following ansatz. And then again, we use the data to constrain the expansion coefficients. The problem with this is that by doing that, you're imposing artificial assumptions about the parametric form of W. And this is especially difficult because they're not, most of the smoothly varying functions are not based in a sound physical theory. And secondly, they're only sensitive to departures from constant density in a very limited space. So you might have a wildly varying equation of state, one that varies quite wildly with time. But the problem is if your parameterization is not sensitive to that particular departure, you won't pick it up, and you'll get a constant equation of state back. But there is one method which does make good way to working around this, and this is principal component analysis. This is essentially where you take a parameterization of dark energy and you rotate it into a basis where the new parameters are uncorrelated. And this is argued to form a much more natural basis in which to characterize the evolution of dark energy. Okay, so if, for example, we start with a piecewise constant equation of state. So this is where you've taken your equation of state and you take the redshift space that you want to constrain it over, and you bin it into redshift bins, and you assume W to be a constant in each redshift bin. So basically, you're now trying to constrain a vector W of n vectors, where n is the number of redshift bins that you have. What you do is you take the covariance matrix and you diagonalize it using a decorrelation matrix, which is W. So basically, you're taking the covariance matrix and you're converting it into you're diagonalizing it, and this is the new covariance matrix of your new parameter set. So because the covariance matrix is diagonal, it means that the new parameters are uncorrelated. The new parameters then form the rows of your decorrelation matrix over here. The diagonal elements of your covariance matrix, they give you the variances on your new parameters.
You have some function, some basis functions for W of Z.
Yeah.
When you mean uncorrelated, that implies that some kind of statistical relationship between these functions, or you're just talking about, you mean orthogonal?
Orthogonal, yes, exactly that. Orthogonal, sorry, yeah.
Okay, so, okay.
Yeah, exactly that. No, sorry. They are exactly that. So your new covariance matrix is diagonal, and therefore, yeah. Yes, it's an orthogonal set as well. Yes. So.
You're talking about constraints. The coefficients of each function are uncorrelated by the data. You
Yep.
can get
Well,
these functions, but now you have coefficients for each function.
Yes.
You have coefficients for, say, a Taylor expansion. And when you fit each of these coefficients to the data, you're not getting decorrelated.
Right. Yes, but by the nature of them being being orthogonal, they are going to be uncorrelated.
They're both orthogonal functions and decorrelated.
So that depends on the correlation function of your data, and how your data points are.
Yes, determined by that matrix C.
But
your imaginary data set, you get a different set of functions.
So it's different from just the functions being, orthogonal to each other when you just integrate them up. Okay.
I'm not sure. Okay. Anyway, so you have a covariance matrix, and the diagonal elements of it give you the variances on each of your new parameters. So that basically tells you how well you can then constrain that particular each of the new parameters. So what you can do is you can rank them in order of increasing variance. So your first few parameters are going to be your well-determined ones, and then your last few ones are going to be your less well-determined ones. And if you plot them as a function of redshift, you'll see that your first few modes are very well behaved, very smooth, and you can see most of the power is concentrated at low redshift. If you look at your very high modes, you'll see that they're very noisy, and the power is generally concentrated at high redshift. So what you can do is you can then reconstruct the equation of state in terms of these new parameters, as shown here. But how you increase in the accuracy is that you use only the first few well-determined modes, and you throw the very badly behaved modes away, and therefore increase in accuracy. So this is a reconstruction from their paper, and this is the original function, and this is their reconstruction. But as you can see at high redshift, you get very small error bars. So what this is telling you is that you have very good information that's telling you that the equation of state is tending towards zero at high redshift, when the actual case is that you have no information there. You've thrown your data away. So it does introduce ill-controlled bias at high redshift.
How many modes are they putting in there?
I think it's 4 or 5. I think it's about 5.
So small,
Well,
because they've thrown away the higher modes that
yeah. So and then, Yeah, exactly. So they've thrown away all the noisy modes, which had generally concentrated their power was at high redshift.
So that error bar isn't like the actual error bar.
No, it's. So how they calculate the error bar is that they then take their variances from the covariance matrix, and they sum over the eigenvectors weighted by the variance, and that's how they calculate their error bars. So of course, your eigenvectors at high redshift are 0, which is why you're getting error bars that are tending towards 0. So it is completely expected.
You take the redshift of beams and get first eigenvector, second eigenvector.
Mm-hmm.
If you take the beams in A and you scale factor of your beams in other variables, you get the same result of eigenvector.
I haven't actually ever seen it done in terms of like the scale factor.
So if you do this, compare the first eigenvector to that one, you take the
Yes, you'll get different eigenvectors for that particular basis, yes.
you will get different eigenvectors.
Yes, yes.
It's not modeling dependent.
No, no, it is, yeah.
No, if you take a redshift beam, or I take the scale factor beam,
Sure.
you compare the first eigenvector.
No, the eigenvectors won't be the same.
If you use W of A instead of W of Z,
Right.
now you're going, your modes are not going to have like a one-to-one correspondence.
No, you're going to get different modes, but then when you sum over, you should get a similar reconstruction back. They'll look different, but when you sum over them,
Numbers of bins, like W of A, W of Z should be the same range.
they should converge.
Yeah, so as n goes to infinity, yeah, you have everything, but if you cut, like the first 3 Z parameterized modes,
As opposed to,
added to the first 3 A parameterized modes, I don't think, when you convert one to the other algebraically, you're going to get.
well, you won't be, you probably won't be retaining the same amount of power or information.
Yeah,
Is that what you're saying? You can also choose a different basis vector.
If the limit is infinite n, though, right? Those two have to.
I tried a 9-redshift beam and 40-redshift beams.
They
Cannot go
didn't-
to the 12-redshift beam.
But how fast does it convert? The next question.
I'm sure they checked and convergence was achieved at 100 bins. I'm pretty sure. But
It's have to convert because
there's you keeping the same data, yeah.
can be represented as F of Z or F of A.
Right, absolutely. Mm. Okay. Anyway, so the point is that even though PCA has never been claimed to, no one has ever said that PCA is brilliant for the reconstruction. We're basically we are trying to improve on the idea here, which is introducing some sort of smoothing. So we do recognize the merits of this technique, and how we want to improve on it is that we want to make the assumptions that control this high redshift behavior absolutely clear, so that in terms of the error bars. And we try to do this, we do this with the maximum entropy technique. Why this technique? Well, it has had massive success in the reconstruction of images and spectra in the past, and the key is under unfavorable conditions. So especially in the cases where you have patchy data that is clumped in different areas. It has parallels with the maximum likelihood method. Your maximum likelihood method essentially seeks the best goodness of fit, so it wants to find the model that reproduces the data as closely as possible. But then you do run the risk of overfitting to noise. So in the maximum entropy technique, basically it seeks an optimum between the ragged distribution, which is very structured, which is mapped out by the data, and a smooth distribution, which embodies your prior information. But I'll have to obviously explain a bit more. And this prevents overfitting to noise, which is something you're always worried about with the maximum likelihood method. And we try and apply it in the most independent fashion possible. So it can be applied in a more model-independent fashion possible. Okay, so as any good cosmologist, we perform the maximum entropy technique within a Bayesian framework, which means we want to determine the posterior probability of a parameter W given the data D. Okay, so we obviously need a parameterization for W. So we want to remain as model independent as possible. So we again take a piecewise constant equation of state. So you take the redshift range over which you want to constrain W, and you bin it into equally sized redshift bins, and you assume W to be constant and independent in each redshift bin. So we now want to constrain the vector W given the data. So the first thing we need is the prior. The prior obviously contains all the information that you have before seeing the data. And the point in which the principle of maximum entropy is brought in is when we actually choose this prior. So the principle states that the least biased prior, which encodes all your prior information, is the one which maximizes the entropy of the distribution while remaining consistent with the data. So why this is appealing to us is that the prior maximizes the entropy, and because the entropy is a measure of uncertainty, it implies that you're applying the prior that makes the least assumptions possible while remaining consistent with the data. So Skilling actually showed this, that for a positive additive distribution, which is the type of distribution we'll be dealing with, indeed it was the case that the most conservative and most least biased prior he could impose was one which was found to be a function of the entropy S of the parameter you want to constrain with respect to a default or an initial distribution. You'll see that it's also a function of alpha. Alpha is just a regulator. It's going to weight the entropy, but I'll have to come back to that after I've explained a bit more. But basically, what I just wanted to see that he found that the least biased prior was a function of the entropy of your parameter that you want to constrain W with respect to an initial distribution, which we call M. So this is the form of it. You'll see that if you plot it, it's essentially a convex function, which has a maximum at 0 when W equals M. Okay, so M, as I said before, is your initial distribution. So what you can see from this is that M is basically your maximum entropy solution. It has to maximize the uncertainty, which means that it has to be your most naive distribution given your prior information. Okay, so it has to be the most uninformative model of the equation of state that you have before seeing the data. But obviously you're wondering, well, what have you chosen for M? I'll have to explain a bit more later, but obviously it depends. The entropy depends on your choice of M. But that's the general form. And you can see it resembles things like your thermodynamic entropy, as well as your information entropy, which is equal to the negative of the log of the number of ways in which you can arrive at a specific W in a Poisson process from an initial distribution M. Okay, so as I said before, it has to be the most uninformative distribution that you have, and intuitively that does, to me, mean smooth. But I'll explain a bit more what we take for M in a bit. Okay, so the second thing we need is the probability of the data given the parameterization, like this. You'll see it's a function of the usual likelihood, or the chi-squared. And this is obviously, you can see from this that this term here is going to seek the best goodness of fit, and it's going to try and find the distribution which best fits the data. So if you then look at the posterior probability from before, you'll see that it essentially reduces to a competition between your entropy, your entropic distribution, and the likelihood. So the likelihood is going to introduce structure into the distribution, whereas your entropy, as I said before, is going to be your least informative distribution. It's going to have a smoothing effect. And this competition is mediated by this parameter alpha. So it's a regulator, and it determines the competition between the data and the model, or the default model M. So you'll see that it's going to seek an optimum trade-off between the ragged distribution, which is mapped out by the data, a very noisy distribution, and a smooth distribution, which is favored by the entropic prior. So obviously, its size is quite important. If you have an alpha that's too big, it's going to cause too much smoothing, and you're going to be losing information. An alpha that's too small means that you're going to be overfitting to noise. So there are various ways people deal with it. Some people take a random value of alpha that they think would smooth to the best to produce the optimal smoothing. Other people basically start at the default model. They choose a chi-squared that they feel fits the real structure in the data, and they move away from the model until that chi-squared is actually reached. We included it into hypothesis space, which means that we're essentially selecting the optimum value of alpha at every point. So we include it into hypothesis space and we marginalize over it, and which means that we get a posterior distribution for alpha. Okay, so you're obviously wondering, well, what is this model? Okay, model, everyone starts screaming because then we're claiming that we're doing something that's model independent, and yet we have a model in it.
So does it mean alpha is not a stationary parameter?
It's not a stationary parameter.
Yeah.
No, so it's included into the hypothesis space. So it means that your data is basically dictating how big alpha is. The error bar. So what I've shown is that the entropic prior is basically introduced to penalize the final probability for unwarranted complexity. So it's to have a smoothing effect, and therefore it must represent maximal smoothness. Now, in the case of images, where this works very well, the default model, your initial distribution, seems a lot more obvious. It's going to be a flat surface, which is equal to the mean of the data. But for dark energy, it's slightly more difficult. So we tried to think, what would smoothness essentially mean in terms of dark energy? Well, we thought that we took this to mean a constant in redshift space, but then there is no immediate and obvious choice for the value of this, for the magnitude of this constant. And of course, any choice is going to reflect a prior belief about the form of dark energy. For example, a model which was W is equal to -1 is obviously going to indicate that before seeing the data, you intuitively think it's cosmological constant. So we obviously looked at a few different models to see the effects. Just one or two things about the actual details of the reconstruction. As I said before, we try to remain relatively model independent, so we use a piecewise constant equation of state. So this amounts to basically decomposing W into a sum of weighted orthogonal step functions, which are then weighted by these parameters C. So you'll see that when we actually sample in parameter space, we're actually sampling over the vector containing these coefficients rather than W itself. And I said that the way in which we apply maximum entropy, we're applying it to a positive additive distribution, which means that the parameters that we're estimating have to be positive. So we have to construct the equation of state with its -2 to make sure that if we wanted to sample an effective W from -2 to 0, we were essentially sampling coefficients from 0 to 2. And we sampled the parameter space using an MCMC, which employed a Metropolis-Hastings method. Okay, so we obviously had to see before applying it to the data, we had to see whether it actually worked. So this involved generating a synthetic data set. So we generated measurements of the diameter angular distance and the luminosity distance, and we added a Gaussian noise with a fixed percentage of the true measurement. Initially, we started with a sigma of 1% in line with predictions, but we do realize that is quite optimistic. So essentially what we've done is we've taken a known equation of state, which is smoothly varying, such as this is the true equation of state. We then simulate data points, which are shown in the blue here, and we clustered them at high and low redshift. So we have the data points. In parameter space, we then go to a point in parameter space. We take the values of the cosmological parameters and the effective W at that point. We generate a complementary data point, and we calculate the chi-squared. And then we also calculate the entropy at that point. And that gives us a probability. So after sampling the posterior probability, we reconstructed the equation of state in the different redshift bins, and we put these are 1 sigma error bars. So you can see that in the case where we have data, the reconstruction tracks it relatively well. At high redshift, it's not as effective, but that's understandable because you are integrating over redshift space. But what is key to this is that, first of all, when you have no data, we see that W does fare quite well. The reconstruction fares quite well. But the point is that the fact that we have no information in these points is reflected by the error bars. So the error bars do blow up when you have no information, and that's where we improve on principal components analysis.
So which data are you using?
This is simulated data. So yeah, this is happening.
In reality, you have something
Of rate of 5.
or
0.5.
I mean, those simulated,
Oh, you mean, yes. No, this doesn't represent something like a true data set. Yes, you do have intermediate measurements, yes.
And are those error bars, decorrelated or
They're relatively uncorrelated. Well, you are integrating over redshift space, so there is we do look at the correlations for the real data, and they're relatively uncorrelated except for 2 bins. And we then increase the number of redshift bins to 20, and we see we don't get that much of a change, so we decided to keep it to 10 redshift bins. Okay, so obviously we're wondering about, is there model dependence, because we obviously have to choose a particular model. The model dependence is going to come out when we have very bad data, because if you've got very bad data, you're obviously going to get a bias towards the entropy. The entropy will win over the likelihood. So we looked at the case of 10% error bars, where we have 2 different models when we calculate the entropy. The first model is shown in red, and this is where we have W is equal to -1. That's an effective W. I actually mean M in this case. I hope everyone realizes. And then we have another case where we have W or M is equal to 0. So this is the second model. We have 10% error bars, and we reconstruct the equation of state in the same way. And you'll find that for the case where we have cosmological constant as our model, we get almost an immediate collapse to the entropy. This is an indication of entropic domination, as is the case at high redshift. We've got a shifting towards the default model. So this is obviously showing clear signs of model dependence. It obviously depends on what you take your prior model to be. And this is especially this poses a problem, especially for the case of cosmological constant, because our data is probably going to look like cosmological constant. So how will you determine a real affinity for W is equal to -1 or merely entropic domination? So what we decided to do is to still keep the model as a constant in redshift space, but then to float the value of the model and to actually include the value of the constant as a parameter in the parameter space. So this about, again, and we marginalize over it. So it amounts, again, to selecting the optimum value at every point. It performs quite well, especially with clustered data, and we get larger error bars, but we feel that the error bars are controlled. Okay, you're obviously introducing more degrees of freedom, but we feel that the error bars are controlled, which is why we then use this. We marginalize over the model for the real data. And we looked at, will we pick up sharp features? The reason that we decided to use the step functions is that provided the binning is fine enough, you should be able to detect sharp features in the equation of state. And we found for this case that we do detect something. We don't reconstruct it very well, but we do detect something.
So I'm just a little bit confused. You have your entropy function, which goes into your choice of prior, and then you've got M is, I guess, do you choose, is that M come from the data itself, or you?
No, the M is your choice.
What? It's a reference model. I mean,
Yeah.
So how do you make that choice?
Well, exactly, but because it forms part of the prior, it has to reflect your prior belief in the equation of state.
So you just guess something.
Yeah, but we don't. We marginalize over it.
Okay.
So we're including the actual value into
Marginalizing over constant?
over constant. So our model is we take it to be a constant range of space, but we let the actual value of that constant float, and we include that as a parameter. So that's, you're going to be wanting to it'll tend towards the mean of the data.
When I look at this figure, it looks like you've ruled out the truth at high confidence, which seems to be not a desirable property.
No, absolutely. And but this is an extreme case. But the point is, you are detecting some structure in the data.
This is an underlying step function. This is not. Right?
There is an underlying step
The
function.
diamond is the truth, right?
Yes. So no, absolutely.
Because her priors that she's using don't allow for this sort of behavior. That's the issue, right?
Isn't the whole point of all of this to
So you're saying that the prior is going to hide the truth of the situation?
Well, right.
No, absolutely.
That may be true, but
This now is the real data.
No, this is still artificial data.
I see. But it's still artificial data.
This is still, yeah.
Right, the blue thing, you see, that blue thing is that step function. That's
So this,
artificial thing, obviously.
this is the truth
There's no real evidence
on the
saying
situation.
that, they're going to use step function.
Yes. Yes?
I think the only way to cure for this is to allow for such a thing as well. You would have again to marginalize over this would blow up your error bar such that again you would be inconsistent, but you can't make any
Exactly.
non-regularizing.
Exactly. That is the whole point of regularizing of it, to improve on your error bars. Otherwise, you get these massive error bars where no one can say anything about them. There are various regularizing procedures, and this is one of them. But yes, no, I completely agree with that. That it does, in this case, it does look like, well, then you've got no chance of actually ever reconstructing the truth. But the fact is, the likelihood is winning to an extent of your prior, and if your prior is strong, and you see this, you know for a fact that is real structure.
And so would you then go back and change your prior?
Yes, exactly, and then it can be an iterative procedure.
So she's supposed to look at this. So she's got those error bars.
But then-
she's supposed to know that she has to change her prior.
No, because
The prior is
I mean-
constant and
It doesn't look constant. Yeah.
well, you can, I guess you could have done it.
But how would you improve on this then? If you,
Also, your choice of prior, I guess, artificially is lowering the error bars, right?
okay, but then, so if you were to take this and you were to reconstruct it with a piecewise constant equation of state, you've got 10 redshift bins, you might get something over here. You're going to get massive error bars that tell you nothing. So what do people do? They fit a constant. This is improving on fitting a constant because it's showing if you fit a constant, you're going to get something like that, which is going to be somewhere in between this. This is saying that in the case where you have good information, fine, let the likelihood win, and you will reconstruct a feature. Principal component. Yeah, well, this is where we hope to improve on it because when you reconstruct in principal components and you throw away modes, your error bars become incredibly misleading at high redshift and they shrink because you have you've thrown away your modes at high redshift. Yeah, this is when they've tried it with the reconstruction. Do you think it should be recovering better? But then with principal component analysis, what do you do about your error bars at high redshift? Oh, okay, all right. Okay. Yes, PSA will be good for low redshift. You are correct there. Okay, I better move on. Okay, so we applied it to real data. We used a shift parameter from the CMB. This is essentially a measure of the diameter angular distance from 0 to surface velocity scattering at 1,100. And it's a good parameter to use because it's independent of the Hubble parameter. This drops out. We also took the HTS key project measurement of the Hubble parameter today and the baryon acoustic oscillations measurement. So prior to recombination, the universe is this pulsating mass of photons and baryons bouncing off each other in equilibrium. When you have recombination, the photons start free streaming. So you've set up acoustic oscillations by the competition between the pressure of the photons and gravitational collapse. Once the photons start free streaming, you're now removing the source, the driving force in your oscillations, and the spatial distribution of the baryons will now preserve the characteristics of the acoustic waves that were set up before. So this provides, and because the characteristic scale of these acoustic oscillations are precisely determined from the peak morphology in the CMB, you now have a standard ruler. So you compare the characteristic scale at high characteristic scale at the period of recombination, and you compare it with a peak in the late time matter power spectrum because the initial perturbations are preserved, and you should see a peak in the late-time matter power spectrum. And this is reduced to a single data point at redshift of 0.35. And then you have the supernova data. They form standard candles because their peak brightnesses appear to be very tightly correlated with the scale of their brightening and their fading. We use two data sets, the legacy survey supernova as well as the gold set from the HHS Goods program. We use them separately because there are systematic differences in the data processing. So when I talk about my two different data sets, basically the only difference between them is are the supernova that I use in the two of them. So my first data set will be the supernova plus baryon acoustic oscillation plus the Hubble parameter and plus the shift parameter, and the same for the gold set. And then we compare them. Okay, so we did the reconstruction. We let W vary from 0 to -2. This is for a default model which has been marginalized over. And we reconstructed it for 10 redshift bins. Ignore the best fit points here, by the way. They shouldn't be there. You'll find that for the supernova legacy survey data, it's pretty consistent with cosmological constant. The large error bars are due to our conservative priors. So it's due to the fact that we're marginalizing over the model, and we're also allowing it a very large range in W from 0 to -2.
What happens if you shrink
your error bars shrink as well because you're incorporating more information. And then we did it for the good survey. The W recovered in the first bin they're relatively consistent, which is good because some of the supernova overlap in these two data sets. A very interesting point, what we found is that at redshift about 0.4, 0.5, we get a peak in the reconstruction, which actually excludes cosmological constant at the 1 sigma level. And then if we fit a constant to the data, we find that we get cosmological constant quite easily, and this shows us the dangers of just assuming W to be constant and fitting a constant. But this is clearly a structure in the data. You'll find that we get the reconstruction tends to go to slightly higher values, which is an indication of entropic domination at high redshift, which is expected. Well, there's obviously some correlation because you're integrating, right? What do you mean? What do you mean by that?
They are correlated. Okay, I thought you said they were not.
Well, they are correlated, but they're as correlated as you expect them to be. But I don't understand how they wouldn't. I mean, so anything where you're integrating, you're going to be correlated. You're going to have correlations, right? But we get an extreme correlation. No, sorry. Well, we checked for correlations that were out of the ordinary, and the only one that we seem to get these are the reconstructed. These are the equation of states in the different redshift bins. So you've got 10 parameters here and 10 parameters here. So we get a very strong anti-correlation between the equation of state in redshift bin 2 and redshift bin 3. And what we think this must be an artifact of the fact that in the third redshift bin, that's where your baryon acoustic oscillation data sits. So this region is very well constrained. So the data is telling you very strongly what W is there. So when you integrate it, when fitting the data point, you're integrating over the second redshift bin. So the very strong information here is forcing a particular value in the second redshift bin. So that's the only strong and unexpected degeneracy. Does anyone say anything? No. Okay, so what happens when you use a stronger prior? So we decided to use cosmological constant as our prior to see what happens. So we're using a default model of m is equal to -1. And as expected, you obviously get cosmological constant with smaller error bars. That's because you're telling the reconstruction that you have more information, you have stronger information, which is incorporated in your prior. So this is actually an artifact of your very strong prior, these small error bars. But the whole point of doing this is that by putting in a very strong prior, any sort of structure that you get out is going to have to be real structure in order to win over the prior. And we found that this peak, although somewhat smaller, definitely survives even when we increase our prior information, which is telling you that that is a real feature of the data and that structure there. No.
And that's
Well,
what
the other data set doesn't.
Yeah, which shows, once again,
Also,
inconsistency.
it's 1 sigma or something, right? I mean,
Exactly. No one's going to start screaming about 1 sigma.
So why do you then say that it's a significant feature? It's not a significant
Well,
Because for various products.
So what's the difference between these two data? Do they actually sort of, what is the difference in dust fitting or?
are they different? Well, first of all, they're not all the same supernovas. They're looking at different supernovae. I don't actually know what systematic differences there are between the two data sets, but this does not surprise anyone. The Reese data is a bit, not dodgy, but it has changed. When I did this data initially, I used the Reese data from 2004 without the new redshift, without the new high redshift supernova. And then when I redid it with the new data set, which supposedly only had 60 extra high redshift supernova, I got completely different results for.
There's also a nonlinearity correction that was not understood in the Nicholas data in 2004.
And now has been corrected for.
Big effect. So it changed the ones that you had from the 2004 data set as well.
Yeah, which is why, I just took their new data set. W in this redshift bin was actually much further way down here and actually excluded cosmological constant to 1 sigma. But the point is that, yes, you can't make any grand statements over this, but it's, if anything, it's saying go and have a look and see what's going on at that point for future surveys.
It's only, I don't know, it's either, if you take that error bar as the usual Gaussian error bar, then it's not even worth mentioning.
Okay.
It's 1 sigma.
But then why, but the point is something is there.
She's just arguing that she's not putting it there.
A noise feature.
Yeah. But if this method is working, that shouldn't be reconstructed.
So obviously because it's an emergent data, the robust seeing is also why it's in the one about the star. It's quite too big, right? So there is no scatter at all. So
Well, that's maybe I
yeah,
just
it's
don't
misleading.
understand how you put the data bars.
How do you get the error bars actually? How do you compute the error bars?
So you look at the posterior probabilities and you find outside. Yeah, they come out Gaussian.
But in sort of words, what do the error bars mean?
So that is the peak of a distribution, and all points that were sampled around that peak contain 68% of the points that were sampled.
What do
But they are correlated, as you can see. I mean,
So you can see that they correlate.
So prior, there was a smooth function, right? Can vary up and down by that much. And that's why I'm sort of reading this.
I get this response all the time. I've done this before, and yeah, I don't actually know what I believe at this point, but it's more about the method, and that survived over the prior. So, but you still think that it could be an artifact of the noise? Okay, anyway, we will move on. And that bin. I had a histogram of they're primarily in this bin. I can't give you an idea of the size. But if we reduce the bin number, so we now incorporating more supernova into the bin where we find this artifact, obviously your stats are improving, so you're now excluding it to 1 sigma, and you're getting a much higher.
If you were to combine all the compounds using the correlations, what would be the significant deviation from -1?
Sorry,
If you were to combine this, for example, these 5 data points using the correlation that you showed, the correlation structure you showed before, what would be the deviation from -1? What would be the significance of it?
So if you remove the correlations
But if you
between,
combine them all.
I don't understand.
So can you go back to that figure with the matrix of the correlations? Okay, like these off-diagonal terms are fairly small, it looks like, right?
Yeah, it's about 20%.
I'm not
Roughly.
even sure on this thing what. It's hard to read exactly the axes.
Oh, okay. So this
It's
is.
the same 10 coefficients. Why isn't it symmetric?
Oh well, no. This is symmetric, but this is just a plotting thing.
It's just a.
Oh, so no. This I just haven't put the colors here.
Oh, okay. So
No, this is just ignore that. No,
Okay.
that's just from MATLAB.
Okay, because it looks like. Okay.
Oh, sorry. Yeah, in the paper it does. I think it does have Oh, well, I actually put the one set here and the other set here. But no, that's just, it would be symmetric otherwise, yeah.
So what is the chi-square of -1 with respect to?
I don't know the chi-squared because we obviously weren't using chi-squared.
You should be able to compute it for this. Alright, so it seems like the bins are correlated, at the 20% level.
Yeah, it's between 10 and 20. Yeah, about 20%.
Yeah, so 5 data points, each of which is like 1.5 or whatever sigma off of 1. I mean, that's how should imply significance. Partial minus 1, you're saying.
Right.
Which is kind of odd. Because,
So you don't believe that then?
well, big sigma.
That is true.
So I can draw I can draw a fit using lambda CDM through those supernova, can't I? I mean, doesn't that fit?
So if you put a constant to it, yeah. You can put a constant.
It's like sort of like 4 sigma, or 2-ish sigma off.
Can you get it to it then? Yeah, it's just within 1 sigma, I think, if you put a constant to it. That's about 0.9 plus minus 1. But this feature of the restate is not unheard of. People have detected a slope in it. There is a definite change that people have picked up on. Okay, so that's the reduced state step. Okay, can I? There's no way you could get a constant through that. Right. So then are you saying that the error bars are misleading? Okay, we'll have to talk about it afterwards. Okay, so we changed our entropic model. So instead of fitting a constant, we now fitted a smooth function. So this is where we have now 2 degrees of freedom for the model. So we're now constraining 2 parameters for the model. And we put this condition to exclude early time domination by dark energy to make sure that match dominates. And it's interesting that the cosmological constant actually doesn't fall for this model within the 1 sigma error bar. But that's in agreement with current literature. Okay, so we're essentially fitting a different model, entropic model, and we find that the results vary slightly, especially at high redshift. You're now getting much stronger deviation towards the model at high redshift. This is the mean model, by the way. And whether you believe that the structure, this feature, actually still comes out, to me it still looks like a feature, but it's obviously less strongly peaked, which means that there's more entropic domination. And maybe it is less of a real feature than we thought. But the agreement between the low redshift results for this model and for constant are encouraging. Okay. So in summary, we developed a method that was based on maximum entropy to reconstruct the equation of state of dark energy in the most conservative fashion, we thought. When we used artificial data sets, the low redshift reconstructions were very promising, but we do get bias towards towards the model at high redshift. And we felt that marginalizing over M does work with manageable loss of accuracy. So you get slightly bigger error bars, but we thought that was manageable. So for the real data, the legacy survey data, we do recover cosmological constant all the way up to redshift 1100, but the error bars do depend on your model and your prior assumptions. So depending on what model you choose, whether you let it be equal to a specific constant or you marginalize over it, as well as your prior assumptions, meaning the range in which you allow W to vary. For the goods data, at about a redshift of 0.4, 0.5, we do get a much higher W, which is preferred to within 1 or 2 sigma, depending on your assumptions. And it does demonstrate, if you believe that's a real feature of the data, it does demonstrate that there is danger with just fitting a constant W. And the reconstructions do tend to be robust against the model that you use in your entropic prior, but that's primarily at low redshift. The merits, we think that it does improve on PCA because the presence of real structure or noise, whether you think it's noise, is indicated by the error bars. So where you have noise or where there is no information, this is indicated by larger error bars. And it's auto-regulating in the sense where they're throwing away modes. They choose how many modes to throw away. We're incorporating our regulator alpha into the parameter space, and we're marginalizing over it. So the uncertainty of your data, the noise, is going to dictate how big alpha should be. And the ethos behind this whole technique is that the reconstruction tends towards our most intuitive estimate of W in the absence of real information with suitable variance. So the error bars are certainly fitting. And it essentially does not require parametric form of W. And for you to work, we thought about maybe changing the expansion coefficients instead of using step functions. We have looked at Chebyshev functions, but they impose artificial and oscillatory behavior onto the reconstruction that's not there. And maybe extending the subclass of models, and maybe using PCA as a model. But I think about that, that's actually not a good idea. And then also possibly using
Why is that not good?
PCA.
Yeah.
Well, because you're still getting bias at high redshift then. Yeah, so it's still, because then it's going to tend toward, at high redshift where there's going to be entropic domination, you are going to get another bias towards something that's probably incorrect. So. And I thought about maybe doing variable size bins in case that there is structure within one bin, so in case you have two sets of supernova that are favoring different things in the same bin, if you assume a constant, you're just going to take the mean. So there might be a preferred configuration of bins, essentially. But again, that involves incorporating more uncertainty, big error bars. But yeah, that's it.
Any more questions?
Oh, it's a cluster. Yeah.
So have you thought about trying to incorporate structure growth constraints?
No, I haven't actually thought about that, but yeah, that would be the next thing to add. Yeah, weak lensing.